Now begin.
My name is Wolfgang K. I just gave an invited talk at the Heteronanocarb Nano conference, and the topic of my talk was graphene oxide. I gave a general introduction into the topic, and I started to elucidate the structure, to give an introduction to the structure, to the chemical structure of graphene oxide, which is quite elusive. And it is in principle a non-stoichiometric, highly undefined structure. That makes it quite complicated to work with this material or to understand it on one side. And on the other side, there are several opportunities. Well, first of all, I started to explain a little bit some experiments we were performing in collaboration on elucidating the structure on a nanometer scale, quasi on an atomic scale, to elucidate the domain structures of oxygen functional groups. And what we were finding out that they're grouped in the range of about tenths of nanometers. Still, that's a big advantage that we know that. Still, there are many open questions to understand better graphene oxide on individual flakes. I'm sure that there will be done in the near future some more tricky experiments to get out more information on this. Nevertheless, despite this undefined structure, we like it very much, graphene oxide, because the oxygen functional groups impart hydrophilicity. We can process it very easily from aqueous dispersions. This is green chemistry at the end. And I would like to consider graphene oxide as an amphiphilic macromolecule with tunable optoelectronic properties, which in this way graphene oxide fully exposes its full potential in the liquid phase. And once we have graphene oxide in the liquid phase, we can develop dispersions or inks, then we can process it. We can process it into macroscopic forms, such as thin films or papers, membranes, and so we can work with it on a macroscopic scale. We bring the nanoscale to the macroscopic world. We can transform it, for example, into electrode materials, which can be used for energy applications, supercapacitors, sensor material. That's a great potential when we can process it directly from the dispersion. On the other hand, and I was giving several examples on the processing into macroscopic assemblies, and some mentioning as well the critical issue of chemisorbed water. And on the other hand, the liquid phase processing dispersions is also good for establishing interactions with other materials, graphene oxide and other materials, to synergetically combine in self-assembly processes in the liquid phase to create novel improved materials. For examples and I gave examples with with nanoparticles of different types, of metallic nanoparticles, semiconducting nanoparticles, or even biological nanoparticles. And as well, I was showing that one can combine it very nicely with conjugated polymers. It's a special class of polymers of great interest for optoelectronic applications. And we can process it as well together from the liquid phase and to create very nice donor acceptor structures whose properties are very well defined already in the liquid phase and are not modified when we transform it into the solid phase, where we need it as interface materials for certain applications. And the good thing as well is we can transform it and we can use it from the water phase, so we can have a green transformation of materials into macroscopic processes using even industrial related processing mechanisms like spray coating, printing techniques, and all this will contribute to the field of novel electro-optical devices or flexible electronic devices and as well contribute to the field of sensor structures and energy applications in the field of supercapacitors. I think that is a great potential in general of graphene oxide, and I hope I could transmit this kind of ideas to the audience, and that's it.
Thank you very much. That was exactly